After installing both TIA Portal and S7 PLC Sim, here we can find their shortcuts, on desktop. In addition, we can find the tool, Automation License Manager, which is used to manage all license of Siemens installed components. Now, let's open TIA Portal, and then let's create the first project. This windows displays the projects recently used. Click on Create New Project to create a new one in TIA Portal. First, we give a name for the project, example, My First Project. Then, we define its path, where it will be stored, example, on the desktop, under a folder. We can see the version of installed TIA Portal, in my case, version 15.1. Once it is done, click on Create to create the new project. Next, click on Configure a device, and then Add new device. In TIA Portal, we can add either a controller, means PLC, or an HMI or PC system. Knowing that we have 4 ranges of Siemens controllers, S7300, S7400, S71200, S71500. In this project, we will work with the 1500 range. So, we open the folder of the S71500, and we select the controller, 15, 11, 1PN. And PN, means that this controller has a Profinet port. When we select a controller, we can see its thumbnail, its article number, its firmware version, and finally an overview of its technical specifications, including port type, memory size, and so on. Once the controller is selected, click on Add to add this PLC to the current project. The project now is well created, and the controller is well added. This window is called Hardware Configuration, or Device Configuration. Here, we can add, modify and even delete any hardware module. Here, we can find the project name, then the folder which contains all items related to the controller. We can rename the PLC station anywhen. You can access to the device configuration anywhen by clicking here on this icon. You can enter to the properties of any module by clicking on it twice, or right-click, then you select Properties. Now, we are going to configure the Profinet port of the controller, so, we double-click on it, and we open the Properties window. On the sub-menu, Ethernet address, we should click on Add new subnet, to activate this Profinet port. Next, we give it an IP address. In my case, I will take the default address, 192.168.0.1. When adding a new subnet, we can see it here, via the network view. Through this network, the controller is able to communicate with any other device that supports the Profinet protocol. Going back to our current project, now we will add 3 modules, related to my existing hardware configuration. 1 digital input module, 1 digital output module, and 1 analog input module. So, we go to Hardware Catalog, and we can type the article number and search for the desired module. Once it is found, we can see its technical specifications. and then, we can drag and drop it to the right slot, according to the suggested blue boxes, which means this module can be inserted in one of these slots. We will do the same thing for the second module, digital output, and the third module, analog input. Once the modules are added to the controller, we can set its parameters, by clicking on the module, and then we open its properties. For the digital inputs or outputs modules, in general, we have no specific configuration. But, when working with analog inputs or outputs, we should be careful, and especially with the signal type for each channel inside the module. Next, we can define the tags for each module. We can go under the section I/O tags. Or, we can define them later, while writing the program code. Now, we finish with the device configuration, and we are going to start writing the program code. We can simply go under, Program Blocks, and then click on, OB1. As default, the programming language is set to ladder, or contact. You can modify the type after clicking on the block, properties, and then, language. In my case, I will write the program with ladder language, this the most common type used. Our task is about to create a code to monitor a lamp, via two switches. The two switches are digital inputs. The lamp is a digital output. The lamp will turn on, only when the two switches are pressed. To create the program, we absolutely need instructions. On the right side, we have a list of instructions. To use an instruction, we can either search for it in the search box, or browse the catalog until we find it. In this section, we can find the favorite instructions, means the most used ones. You can add yours, by finding your favorite instructions, and then, drag and drop it here. This is an option that allows you to gain time, and directly use instructions, instead of wasting time to find each one. This is the electrical schema of the lamp, and the two switches. If we close the two switches, the lamp will be powered by the 24 VDC and it will turn on. If one of the switches is open, it will cut the power and then the lamp will turn off. We first insert a normally open contact. The activation of the normally open contact depends on the signal state of the associated operand. When the operand has signal state 1, the normally open contact closes and the signal state at the output is set to the signal state of the input. When the operand has signal state 0, the normally open contact is not activated and the signal state at the output of the instruction is reset to 0. Next, to command the lamp, we insert the instruction called assignment. You can use the assignment instruction to set the bit of a specified operand. If the result of logic operation at the input of the coil has signal state 1, the specified operand is set to signal state 1. If the signal state is 0 at the input of the coil, the bit of the specified operand is reset to 0. After inserting the instructions, now it's time to define the tags. We enter first the name of the tag, click Write, then, define tag to create it. Under Section, focus on these three categories. Global inputs means physical inputs. Global outputs means physical outputs. Global memory means internal tags, or mementos. So, the switches will be defined as global inputs, because they are physical, and then they will be wired to the digital input module. On the other hand, the lamp will be defined as global output, because it is physical, and then it will be wired to the digital output module. The PLC will read the state of the switches, and for the lamp, the PLC will monitor its state, depending to the program. All defined tags are stored inside a table, called default tag table. Each tag is defined by its unique name, data type, and its unique address. To facilitate the simulation of this program, we can add, for every switch, an internal tag, to simplify its monitoring during simulation. So, we will add two normally open contacts, and we will add them in parallel. For every switch, we create its proper image, and we will define this image as internal tag, because it is not physical, it exists only inside the PLC memory. So, these two tags will be defined as global memory, their addresses are auto-generated. Now, we finish with writing the program code, it is time to test it. First, we will download it to a real CPU, and then we will download it to the PLC sim. To download the program to a real connected PLC, we can click on the PLC folder on the top, next click on this icon. Or, we can go under, Online, and then click on, Download to device. An extended download screen is open. Here we can set the PGPC interface, means the connection type between the PC and the PLC. On the top, we can see our configured controller, with its subnet, and its IP address. Next, the PGPC interface is set to PN, because our controller has a Profinet port. Next, when working with a real PLC with PN port, here we should select the network card of the PC. Finally, select the subnet of the controller, it is already explained before in the device configuration. When setup is finished, click on Start Search, to make the PC search for the connected controller. Through the Choose an interface. In this list, we can see how many connected devices the PC has found. And below, we can check the status of the searching operation. Now, we can see that the PC has found the real PLC. We can now click on Download, to download the offline program to this controller. Before the downloading operation, the TIA portal always compile your program to check for errors. If there is no error, the program will be successfully loaded to the online controller. Once it is done, we can next enter online with the CPU. To do that, we can either click on Go Online, or, under the top menu, Online, click on Go Online. These green circles on the left side show that we are online with the controller, and the blocks offline and online are similar. We can also enter online with the device configuration, to check if our configured hardware is the same as the real one, or not. If, for example, you want to modify anything in the device configuration, you should click on Go Offline. Now, let's go back to our code, and let's enter online with the main program, OB1. To get all informations about the online controller, we can enter here, under Online and Diagnostics. Here, we can modify the PLC mode, either stop or run. The stop mode is indicated by the orange LED. In this mode, the PLC is not cyclically running through your application code. But, the application is still here. The run mode means the PLC will cyclically run through your application code, read the input state, and command the outputs. This mode is indicated by the green LED. Next, we can go under General, Diagnostic Status, and then Diagnostic Buffer. Under Diagnostic Buffer, we can read all the PLC messages, including the passage from a mode to another, or if there is any problem in the hardware part, or even in the application code. Also, we can see online the cycle time of the PLC, which depends on the application size, and even on the conditions inside. Next, the state of PLC memories. The test of our code consists on changing the state of inputs, and check if the output state will change as we want or no. It is not easy to modify the physical input state, because, simply, the PLC reads their state from the digital input module. That's why we inserted in parallel internal tags, which is more easy to change their state during the test procedure. To modify the state of an internal tag, we simply right-click on it, and then click on Modify to 0, or Modify to 1. We are going to modify the two switches to 1, and check if the lamp will turn on or not. To visualize the final state of tags, it is highly recommended to add a watch table. There, we add all the tags we want to visualize, and then we simply enter online with this table. We can select a tag by entering its name, or its address. We will select the two physical switches, the two images of the switches, and finally the lamp. Through this table, we are able now to check if your code is correct or not. By forcing the two M switches to 1, we can see that the lamp will turn on. If one of the M switches is forced to 0, the lamp will automatically turn off. As we said, it is highly recommended to use the watch table to visualize the final state of the tags and to check if your code works correctly or not. After forcing the internal tags, we will learn now how to force the physical inputs. To do this, we should use the force table, and we can find it here. Here, as usual, we define which physical tags we are going to force. In our case, the two switches. Under Force Value, we can enter to which value we want to force each tag. Next, click on this icon, to activate the forcing of selected tags. We noticed that, on the top on the forced tag, there is a letter, F, means this tag is actually forced. We can also select the second switch, and force it to 1, following the same steps. As we see before, when forcing the switch's state to 1, both, then the lamp will turn on. When working with the force mode, a yellow LED is turning on, showing that a force job is actually enabled. When finished with the force job, you can click on this icon, to end with forcing the selected tags. Now, we are going to go offline with the real connected controller, and we will test the program via PLC Sim. To open the simulator, we can either click on this icon, or we can go under Online, and then click on Simulation, Start. Knowing that with the PLC simulator, you have the same functionality as you would have with a real hardware PLC. Click on OK. The simulator will pop up. It has the same dashboard as a real controller. The extended download screen is open. We set the same parameters as we did with a real controller. The only difference is, we should select PLC Sim instead of selecting the network card of the PC. Once it is done, click on Start Search, so that the PC will search this time for the online PLC Sim. Once it is found, click on Upload, to download the offline program to PLC Sim. When downloading is finished, you are asked to turn your virtual PLC into stop mode, or run mode. We will choose Start the module, to activate the run mode. In the PLC Sim dashboard, we can find first, the name of our controller and its type. Next, we can see its actually IP address. And then, we can change the active mode to run or stop via these two buttons. The third button, mres, will erase the loaded program from the PLC Sim. Now, there is no difference between testing the program with a real controller, or through PLC Sim. We can enter online via this icon, and start the simulation job. First, we enter online with OB1, and then, as usual, we open the watch table, and the force table. We can now be sure that before downloading our code to a real controller, we can first test it through PLC Sim, cause both have the same behavior. Until now, we have learned how to create a new project in TIA Portal, how to add a controller and then configure its port. Then, we have learned how to create a program and how to test it via a real controller, or via PLC Sim. There is an important thing we should learn before going to the next lesson: how to address tags in TIA Portal. To understand what does it mean I0.0, I0.1. And then M0.0, M0.1, and finally, what does it mean Q0.0? The switches, and the lamp are defined as a Boolean tags. The Boolean is the basic element, it contains the value 0, or 1. Its size in memory is 1 bit. Now, we learn the first data type, the Boolean. Now, let's have a zoom in inside the PLC memory. The PLC stores the tags in 3 categories. The first category is reserved for the physical inputs, letter I, or E, and E means Enneagung in German. From top to bottom, we have the number of bytes, from 0 to n. N depends on the max size of PLC memory. From left to right, we have the number of bits, starting from 0 to 7. So, the basic element is the bit. A group of 8 bits make a byte. In our program, we have defined the 2 switches as physical inputs. The PLC stores them inside the I category. The first switch will take the address 0.0. The first 0 means the byte number 0. The second 0 means the bit number 0, inside the byte number 0. As the first bit is reserved for the first switch, the second switch will take the next empty place in memory, means address 0.1. Means the bit number 1, inside the byte number 0. If, for example, we want to add a third switch, or any other Boolean physical input, it will take automatically the next empty address, means 0.2, and so on. We learned where and how the PLC stores the physical inputs. Now, for the physical outputs, we have the second category inside the memory. It is called Q, or A. The lamp tag will be stored inside this category, in the first empty address, means 0.0. If we want to add another Boolean physical output, it will automatically takes the address 0.1, and so on. Finally, the third category will contain the internal tags, or mementos. The first M switch tag will be stored in the address 0.0. The second M switch tag will be stored in the address 0.1. And if we want to add a Boolean memento, it will automatically takes the address 0.2, and so on. Now, we learned how to address tags in TIA Portal. To sum up, when addressing a tag, we should first specify its category, I, Q, or M. Next, we enter the byte's number, then the bit's number inside this byte. For example, we have a tag which is stored with the address M3.0. Means, this tag is an internal tag, and it is stored inside the bit number 0, inside the byte number 3. When we go back to our project in TIA Portal, and when we open the default tag table, now we are able to understand which means every address for each tag, and while reading the address, we can directly understand if it is a physical input, a physical output, or it is just an internal tag. Now, let's move on to another section. In this section, we will have an application, which consists on managing a simple traffic light, with 3 lamps. With this application, we will learn how to write a sequential program in TIA Portal. When talking about a sequential program, we always use the graphic tool, GraphSet. It is a powerful tool that describes the steps of the sequence, and the transitions from a step to another. In our application, this is the GraphSet of our system. We have 4 steps, starting for the initial step. In each of the other 3 steps, we will command every time a unique lamp. Every lamp will turn on during a preset time. The cycle will start when the user clicks on the Start button, in the HMI side. If he wants to stop the cycle, he can, anywhen, clicks on the Stop button. During the initial step, the system is in sleep mode, all lamps are turned off. With the step number 1, the red lamp will turn on, for 2 seconds. With the step number 2, the yellow lamp will turn on, for 3 seconds. And finally, with the step number 3, the green lamp will turn on, for 4 seconds. So, we need a tag which will contain the active step. This tag value may be 0, 1, 2, or 3. After understanding the system logic, we are going to write the program code in TIA Portal. Let's continue with the same previous project. We can continue writing the new code in OB1. But to make your program more organized, we can use the function. The function is often used to divide your program, and make it more organized and clear. To create a new function, you can simply click on Add a new block, and you choose FC or function. We give it the name, FC Traffic Light. This function will contain the part of the program that is about the traffic light system. We can choose the language of this function through this list. In our case, we will continue with ladder. Once it is done, click on OK to create this function. The new function will be classed under program blocks. During the execution of the program by the controller, this FC will not be executed, because it is not called in the main program OB1. To do this, we can simply drag it, and drop it inside the main program. So, the controller executes cyclically the code inside the OB1. When it arrives to this network, it will open the function and executes its inside program part. Now, we will open the function, and start creating the program for the traffic light system. The system has three outputs: the red lamp, the yellow lamp, and finally, the green lamp. We should first create these three tags in TIA Portal. They will be stored in the physical outputs category. To do this, we can either create it inside the default tag table, here, or we can define it directly through the digital output module, in the device configuration, under the section, I/O tags. We select this DO module, we click Right and then enter on Properties. Here, we can define the three new tags for the three lamps. We give it the names, TL lamp red, and TL like, traffic light. Then, TL lamp yellow, and finally, TL lamp green. We can in parallel, open the default tag table. When defining a new tag in any module, this tag is automatically saved inside this table. Once the tags are well defined, let's go back to our function, and let's start creating our code for the traffic light. As we mentioned before, we need to create an internal tag to keep in memory the active step. Its data type will not be Boolean, but integer, because its value can be 0, 1, 2, or 3. We can create any tag through the default tag table, or we can directly define it when creating the program. In our case, we will insert the instruction called comparator, and we will enter the name of the new tag. We will give it the name, mActiveStep, and m means memento. Then, we right-click on it, and we define its data type as integer. As default, any memento tag will take the value 0 when the PLC starts executing the program. So, the tag mActiveStep will be 0 first, means default active step is 0. To understand this step, in this network, we will teach the PLC how to do the transition between step 0 and step 1. As default, the active step is 0. If the user will click on Start Cycle, then, we should jump to step number 1. So here, the conditions to jump from step 0 to step 1 are: step 0 is active, and the start cycle is pressed by the user. That's why we inserted a comparator, and next, a normally open contact to check if the key is pressed or not. The start cycle tag is not defined yet, so here, we enter its name first, click Right, define it as a global memory, then we press OK. When these conditions are true at the same time, as result, we should jump to step number 1. In other words, we should update the value of the tag mActiveStep from 0 to 1. To do this, we will use the instruction called move. Through this network, we teach the PLC in which conditions we should jump from step 0 to step 1. Now, we suppose that actual step is 1, so, we will teach the PLC in which conditions we can jump from step 1 to step 2. Like we did in Network 1, we suppose that actual step is 1, and next, the transition will be a timer. So, first, we insert a comparator, and we compare the tag mActiveStep with 1, and if it is true, we will use a preset timer as a transition. To find the timers, we can go under Folder, Timer, Operations. We are going to use the type TON. On delay timer will becomes on after a particular time delay. In other words, this timer will delay the activation of the next step, and during its working operation, the output of the actual step is still turned on. To understand it more, look at this picture. When switch is off, the timer is not active and as a result, the lamp is turned off. Once the switch is pressed, the TON timer becomes active and starts counting 3 seconds, the preset time. The timer output is off, the lamp is still off. When the preset time is elapsed, means after 3 seconds, the TON timer output will be active, and as a result, the lamp will turn on. We can understand now, what does it mean on delay timer? Going back to our code, and when we insert this timer, a pop-up will appear. This block demands an instance data block, we will explain it later. Now, just hit OK to insert the timer. In the input parameter, PT, here we enter the setpoint time value. We enter 2s, means 2 seconds. When these two conditions are true, at this time, we should jump from step 1 to step 2. As usual, we call the instruction move, and we update the value of the tag mActiveStep from 1 to 2. Through this network, we teach the PLC how to jump from the step number 1 to step number 2. The next network will be how to jump from the step number 2 to step number 3. And the final network will be about how to go back from step number 3 to the initial step. When the active step is 2, and after a preset time equal to 3 seconds, at this time we jump to step 3. We will do the same as the previous network. Just be careful while using the timers, do not do a copy-paste. Here, we compare this tag with 2. Here, we insert another timer, and we enter 3 seconds as a preset time. And finally, we update the value of active step using the move function, from 2 to 3. The final network will be about how to jump, or in other words, how to go back from step 3 to step 0. With this network, our graph set will be completed. So, through this network, we will teach the PLC if the active step is 3, and if timer TON will complete its preset time, 4 seconds, at this time, we will jump to step 0. We start with the comparator, here the PLC checks if active step is 3 or not. Next, we insert a new timer TON, and we set its PT input to 4 seconds. Finally, we use the move function to update the tag mActiveStep from 3 to 0. It is usually recommended to write a comment for each network. As a result, your program will be more organized. You can through this icons open or close all the networks. The last thing to do is the cycle stop. When the user click on the stop cycle button through the HMI, the system should stop. In other words, we should force the tag mActiveStep to 0. The cycle stop tag is not yet defined. We will define it here as a memento, means global memory. The normally open contact will check if this tag is true or not. If yes, means if the user decides to stop the cycle through this button, we should move 0 to the tag mActiveStep. Now our code is ready for simulation. We will click on this icon, as we saw before, to run the PLC sim. I will go fast through these steps because they are known. Sometimes this pop-up appears. Don't worry, just close the function, and then open it again. Now, the program is well loaded to the PLC sim, we are online and now we start the simulation of the code. To test our code, we are going to create a new watch table. In this table, we will select which tags we want to visualize. When working with a sequential program, the most important tag to check is the active step. In addition, we will add the two HMI buttons, stop cycle, and cycle stop. We enter online with this watch table. As we can see, as default, the active step now is 0. We are going to start the cycle, and checking the smooth running of the sequence. The start cycle is an HMI push button, means we should force it to true, then fastly force it to false. When pressing this button, we can notice that the sequence jumps from step 0 to step 1. After 2 seconds, it jumps from step 1 to step 2. After 3 seconds, it jumps from step 2 to step 3. And finally, after 4 seconds, it goes back from step 3 to step 0. We can enter online with the function and visualize, in real time, the jumping from step 3 to step 0, through the timer, T-on. After checking the smooth running of the sequence, the last thing to simulate is the stop cycle. At any time, when the user presses the stop cycle, the system should goes, from any active step, to step 0. Finally, we can say that your code works correctly. The last thing to do is to command the outputs. It is the simplest task, because each of the lamps depends on its related step. We will see how to do it. Simply, we insert the comparator instruction, and we check. If the step 1 is active, then we insert an assignment instruction to turn on the red lamp. By this way, the red lamp turns on, only when step 1 is active. During the other steps, it will turn off. We do the same for the other lamps. The yellow lamp will turn on only when step 2 is active. The green lamp will turn on only when step 3 is active. When you modify anything in your code and you want to test it, you should download it again to the PLC sim. Once it is done, now we can add these 3 lamps to our watch table, starts the cycle, and see what will happen. As usual, we enter the tags here by entering its name, or its address. Through this table, and when starting the cycle, we can see that every lamp will turn on, only when its relative step is active. Now, we can say that we have successfully created a sequential program in TIA Portal. Now, we will move on to another section: how to insert an HMI station in my project. Until now, our project has a single PLC station. To add another PLC, or to add an HMI station, we can simply click on Add New Device. Through this window, we can choose which device to add, either another controller, an HMI station, or a PC system. In our case, we will add a Siemens panel, called TP900 Comfort. The abbreviation of TP means touch and panel. When we click on it, we can see on the right its thumbnail, its article number, its firmware version, and finally an overview of its technical specifications. The first thing we should focus on, when adding an HMI to a PLC station, is the communication protocol. It must be the same for both. Our PLC has a Profinet port. This HMI type already has a Profinet port, so these two devices can communicate. Once it is selected, click on OK to add this HMI to this project. A new wizard has appeared. This can help us to integrate the new HMI station. Through this interface, we can choose with which PLC this new panel will communicate. When we click on Browse, a list of existing PLC in this project will appear. We already have a single controller, the 15.11.1 so we will select it. Since the PLC and the HMI are now connected, the other options in this wizard are not important. We can customize our HMI station later, but let's have a look. The next parameter is Screen Layout. Then Alarms View. Then, Screens. Here we can add on other screens from here. Then, System Screens. And finally, Buttons. Once it is finished, click on Finish to add this panel to this current project. In the project tree, we can notice that, in addition to the PLC station folder, the new HMI station folder was successfully added. To check if the PLC and the panel are well connected or not, we can go under Device and Networks. Here, we can make sure that both devices are now connected, through the PN subnet. Now, we can go back to our HMI station and start our work there. We can anyone rename our HMI station. In my case, I will give it the name, My HMI. As default, there is no tag defined yet in the HMI default tag table. The two devices are connected, but PLC tags will be imported here manually, one by one, and on demand. Under the sub-menu, Connections, we can see the HMI connections table and the details of each one. You should know that an HMI can communicate with more than one controller, and with each one, he can exchange different tags separately. Now, and under the sub-menu screens, let's open the default screen and then let's rename it. We will give it the name, Traffic Light Screen. At the top of the screen, there are existing elements as default, like the logo of Siemens, the screen name, and the date and time field. These elements are not created through this screen, but rather, they are created through the template. We can find the default template under the folder, Screen Management. With the template, we can create elements just once, and then use them directly in any screen we want. To make the screen name dynamic, we can use the existing field in this template, and then we can go under Text and Graphic Lists, and there, we can define the list of screens name in this project. Now, we start creating our first screen in the HMI station. We want to add two buttons, the first for the cycle start, the second for the cycle stop. We can find the button element under Elements. To edit the button properties, we can simply right-click on it, then select Properties. First, we can rename it. We can give it the name Start. In addition, when we talk about button, we talk about action to do, or in other words, events. So, we go under the submenu, Events. While pressing this button by the user, we want to create an event. In our case, we want to force the tag, mStartCycle, to the value, 1. To choose the event, we have a drop list. We go under, Edit Bits, and we select, SetBit. When choosing this event, we are asked to select which bit to force. So, we click on, Browse. In this window, we have the two existing stations, both PLC and HMI. Since this tag is not copied yet from PLC to the default tag table in HMI, we should browse the PLC tag table, and select it. When pressing OK, this tag will be automatically copied in the HMI tag table. Next, we have another event that we should add, this time when user releases this button. We want to reset the tag, mStartCycle. To do that, we will choose the event, RASBit, and we select the same tag. Since this tag is now copied in the HMI tag table, we can insert it here directly. We finished with the button events. Now we will animate its background color when it is pressed. We go under Animations. This option is used to make sure if this button works properly or not, in other words, if he is really forcing the related PLC tag or not. So, we click on Dynamize Colors and Flashing. We are asked to select through which tag we want to make the button background dynamic, and, by logic, we will select the tag, mCycleStart. After selecting the tag, now it's time to choose a background color for each value of this tag. If it is 0, the background will be gray. If it is 1, the background will be green. We finished with editing the properties of the first button, Start Cycle. Now, we are going to add a second button. Its name will be Stop. To gain time, we can do a copy-paste and then change the properties. As we said, here we give it the name, Stop. Next, we keep the same events, and we have just to change the tag. Now we will force the tag, mCycleStop. This tag is not yet copied from PLC tag table to HMI tag table. So, we browse the PLC station and we select it. Under Animations, we will keep the same background colors. Here, we are going to just change the tag. The two buttons are now ready. Let's move on to insert a picture. We can find it under Basic Objects. We will browse our computer, and select a picture to this screen. Under Properties of this picture, we have some options we can use, like Style, Width, and Background Color. The next step is, we want to add a circle for each lamp. And then, we will animate it through its related tag. The circle can be inserted via Basic Objects menu. Once it is inserted, we go under Animations Properties sub-menu. We click on Dynamize Colors and Flashing to create a new animation. For the tag, we do a browse as usual to copy the tag from PLC to HMI tag table. For the red lamp, we will select its related tag, TL lamp red. After selecting the tag, we will dynamize the background color. Gray, if the lamp is turned off. Red, if the lamp is turned on. For the other two lamps, we can do a copy-paste, then we will change the properties. We can click on these icons, to align or justify different objects. For the second circle, we will keep the same properties and we will only change the related tag to TL lamp yellow. Then, when this tag is 1, we will change the background color to yellow. We do the same thing with the third lamp. Its related tag will be TL lamp green. For the background, we will choose the green color when the tag state is 1. We finish with the design of this screen. Now, let's run the simulator for the PLC station, and next, let's start the runtime of the HMI station. The HMI runtime allows to run the application as it's as Unreal panel. To launch the HMI runtime, click on the HMI station folder, and then click on Start Simulation. The TIA portal first compile your HMI station program, and then, if there is no error, the runtime will be launched. Here is the first look of our screen in runtime. Let's retest the traffic light sequence, via HMI. We will click on Start, to start the sequence and let's see what happens. We can see that the first red lamp turns on during 2 seconds. The second yellow lamp during 3 seconds. The third red lamp during 4 seconds, and then the cycle stops. When we hold press on the button, we can see that its background becomes green. It means the related PLC tag is toggled to 1. We often use this trick to check if the button works correctly or not, and also to check the communication between the PLC and the HMI. We can open the PLC watch table and the runtime, both at the same time, to see what happens when we press on the HMI buttons during the runtime. We can see that the mStart cycles tag will be toggled to 1 when we click on the button, then it will be 0 when we release it. Through these tests, we checked that our code works properly, either on PLC side, and HMI side. Now, we move to another thing. We want to make the user changes the preset times anywhen he wants, and to do this, we should change the PT inputs of the timer, from constant value, to a tag that can be modified next through HMI. To do this, we can define a new tags as global memory, or mementos. But we can also define them in a data block. A data block is an area of memory that can be freely set up for any type of data you like. This can be bits, bytes, words, ints, reals, or even your own data types. The size of the data block depends on the PLC. To create a new data block, we can simply click on Add New Block, and then we choose Data Block. We will give it the name, settings, and we can change its number or leave the default one. When we click on OK, the new data block is well created, and we can find it here, under the folder, Program Blocks. This is how it looks, exactly like an Excel table. We have another tool that helps us to make our blocks more organized. We can create a group, or in other words a blocks folder. Inside this group, we will move any block which is about the traffic light system. Now, inside the new data block, let's create the new tags, for the 3 preset times. First, we enter the new tag's name, then we select its data type, that is all. In our case, these 3 tags will take time as data type, because the timer's PT input demands a time data type. Here, we have an option that we can use it is called Start Value. As default, all tags values are 0 because they are internal tags. This option allows to assign an initial value to a data block variable, when the PLC changes its mode from stop to run, or when it starts up. In our case, we will choose any random values, like 1, 1, and 2 seconds. We should use the right syntax. T, then, hash key, then preset time, then the unity, example, milliseconds, seconds, minutes, hour, and so on. Once tags are created, it is time to assign them. We can simply drag them one by one, and drop it in the right place. Here, we assign each tag to the PT input of each timer. When we want to use directly a data block variable, we can simply click once on this block, then click on Details View. The data block will be accessible and we can drag any variable we want use in the program. After downloading the modifications to the PLC sim, we can enter online with the program code, and also with the data block, we can see that the actual values are the same as configured start values. The tags are well assigned in the PT inputs of each timer. Our task now is to create a new screen in the HMI station. In this screen, we will allow the user to change these parameters for each timer, any when he wants. To do this, we will open the HMI station folder, and then we click on Add New Screen, then we give it the name, Settings. We first insert a static text, we will click right on it, and under General Menu, we can rename it to Setpoint Time Lamp Red. We can change the style text and its size. Next, under Elements, we will insert an Input-Output field. Then, we will assign it our desired PLC tag. Since this tag is not yet known in the HMI station, we will browse the PLC station folder, open the data block, settings, and then select the related tag. Here we can set the format pattern, means how many digits can take this input-output field. Next, we can choose through this drop list, if this I/O field is an input-output, means the user can change it when he wants, or it is an output field, means the user has not access to change it, he can only see its actual value. In our case, we will choose it as an input-output. We will do the same thing for the two other parameters, for the yellow lamp, and then for the green lamp. Once we have finished, we can start the simulation. We notice that we cannot access to the settings screen from this screen. To do this, we need to add a new button, which allows us to open the desired screen when clicking on it. So we go under Elements, and we drag and drop a new button. We give it the name, Settings. Under Events, and through the drop list, we can choose the event, Activate Screen, and then select which screen we need to open. We can directly enter the screen's name, or, we can select it through the drop list, or also, we can drag the desired screen and then drop it. We will do the same thing when we are inside the settings screen. We should add a button that allows us to go back to the home screen, when clicking on it. To gain time, we can copy-paste, then we can change the properties. We will give it the name, Home Screen. We keep the same event, and we have to change only which screen to open. Through this button, we want to activate the screen, Traffic Light System, or we can call it Home Screen since it is the startup screen. When we simulate our HMI station, we can now jump from a screen to another, through these new buttons. When you see these hash keys in any I/O field during runtime, means that this field is not connected with the related PLC tag, or, the format pattern is incorrect. Let's go back to the I/O field properties and change the pattern format. We will add another digit to each of these three I/O fields. After starting the simulation, now the I/O fields are well connected with the PLC tags, but the values seems to be incorrect, since we are expecting the values 1, 1, and 2. There is a simple trick when working with the data type, time. The PLC uses the milliseconds as its default time base. In our case, we need the preset times with the base time, seconds. So, we need to do a scale between the value we write in HMI, and the value stored in the data block. To activate this scale, we will open the HMI default tags table, and we click right on the related tag, and then we select Properties. We open the sub-menu, Linear Scaling, and we check the box, Linear Scaling. To make it easy to understand, when we write the value 1 in this tag's I/O field, we mean 1 second, so the PLC should receive the value 1000, means 1000 milliseconds, means 1 second. We will activate the same linear scaling for the other two tags, which are setPoint timelamp red and setPoint timelamp yellow. After starting the simulation, we can now be sure that when the user enters a value in one of these I/O fields, its time database will be in seconds. After creating and testing our code in the PLC station, now we finished with designing our two screens in the HMI station. The system is ready, and the user can change the parameters, and can easily monitor the traffic light system. Now, let's start with adding the new physical signals in the device configuration. There, we will add the two analog signals coming from the PT100, and also the two heaters resistors. To add an analog input to the project, we need an analog input module. This module works as an analog to digital converter. It converts the analog signal coming from the transducer, and then convert it to a digital signal, which can be treated by the controller. In this actual hardware configuration, we already have an analog input module. Let's click right on it, and then, via its properties, we will configure it and add the two new analog signals. This module supports 8 channels. Each channel, or in other words each input, can has its own configuration. We mean by the configuration, the signal type sent from the transducer to this module. This module, for example, can read a voltage signal, a current signal, an RTD signal and even a thermocouple signal. It is more expensive than the other modules that support just one signal type. In our case, we are going to configure the first channel, to enable it receiving a current signal, which varies between 4 and 20 mA, and will be connected with 4 wires. So, in the measurement type drop list, we will select current, 4 wires transducer. Next, we will select 4 to 20 mA through the measuring range drop list. And we will configure the second channel the same manner. The channel template is just an option, you can use it when we have the same configuration for many channels. Instead of repeating the config for each channel, you can simply define it through template, and then apply it for any channel you want. Then, and through this sub-menu, we can find the starting addresses for analog inputs of this module. We can leave the default ones, or we can change it, providing that the chosen address is empty. For example, we can choose 10 as a starting addresses. Here, we can find the 8 channels, each with its related address, starting with the choosed starting address. We should know that the letter W in these addresses means word. In other words, each analog inputs takes 16 bits in the I area category. Its data type is integer. Here, we define the name of the first analog input. We give it the name, int temperature bath1. And we write, int, because the data type here is integer. We do the same for the second analog input, we give it the name, int temperature bath2. Now, let's move on to the digital output module, click right and then select Properties. Under I/O tags, we will define the new DA tags. We will give it the name, heat resis bath1, and heat resis bath2. The configuration of the new physical signals is finished. Let's go back to our code and start creating the program for the temperature control system. We can work directly under OB1, or, as we did in the previous chapter, we can create a new function, and put this new code part there. We rename the folder to temperature control. Then, we will create a new function, and give it the name, FC temperature control. When adding a new function, we don't forget to call it in OB1. We can simply drag it and then drop it here. During the execution of the main program, the controller finds this new block and then executes the code part in it. Let's open the new function, and start creating the code. In this system, we have two similar baths, and the word similar means, both have the same temperature control logic. So, instead of repeating the code twice, we can use a template, called function block, or FB. The FB can be used to simplify the process of programming. Basically, it is a means of reducing the programming length and complexity written by the programmer. To create a new function block, FB, or template, we can simply click on Add New Block, and then we can select FB. We give it the name, FB Temperature Control. When clicking on OK, the function block will be successfully created. We can find it here. When working with the FB, we usually use local tags, and not global tags. The local tags are created and used only in this block. The global tags, on the contrary, can be used anywhere in the project. The local tags can be created through the I/O table of the function block. The first instruction we are going to use is scale. The scale instruction is used to convert the integer value of the analog input into a floating point number which can be scaled in physical units between a low limit value and a high limit value. We can search it through the search box. Once it is found, we can drag it and then drop it here. When you need to see all details about any instruction, you can click on it and then hit F1. Here, we can find all the necessary informations about the scale instruction. And here, we can see the equation which is used by the scale function. Also, we can see all the input-outputs parameters, their description and their data types. The first input parameter is the in. Here we should assign which analog input we are going to scale. We can simply start writing the tag name, and the TIA portal automatically starts suggesting the related tag names. Here, we assign the temperature signal of the first bath. But, don't forget that we are working under the function block, which is used here as a template. The template will be shared next with the two baths. So, instead of using a global tags, we will use the local tags. We can use the I/O tags table of the function block to create the local tags. We start with the first input, the temperature of bath X. Here we didn't say bath 1 or bath 2, but rather, bath X. As we said, its data type is integer. Once it is defined, next we will drag it and assign it to the scale input in. Now, let's make a pause, and go back to our function, FC temperature control. When the function block is created, we will use it twice. Once for the temperature control of the bath number 1. We simply drag the function block and drag it here. A pop-up will appear. It said that we should define an instance block for this FB. This instance block will serve to store all the parameters values used by this FB. We can rename it, and then click on OK. This is the first call of our function block. It is called with its related instance data block. As you can see, on the left, there is an input, called int temperature bath X. In each use of this FB, we will assign a temperature value for the related bath. And this data block is the instance DB related to this call of the FB. Let's split the screen and go back inside the function block, FB temperature control. If we want to use this function block for the bath number 2, we can, as usual, drag it and drop it in the next network. The two baths use the same template, means the same function block, but there is no overlap between them. With every call, we will assign the related inputs-outputs for each bath. When calling the function block, we are asked again to add a new instance block, now for the bath number 2. We can give it a name, and then click on OK. Going back to our template, in the high limit and low limit inputs parameters of the scale function, we should enter the measurement range of the measurement device. In our case, the PT100 range is between 0 Celsius degree and 250 Celsius degree. The next input parameter is bipolar. We should enter a tag which is always 0, if the analog input is unipolar, or a tag always 1, if the analog input is bipolar. In the hardware config, if the analog input is set up as plus or minus 10 volts for example, it's bipolar. If the card is set up as 4 to 20 mA or 0 to 10 volts, it's unipolar. To enter a tag which is always 0, or always 1, we can use the system memory bits. We can click right on the PLC station, select Properties, and then open the sub-menu, System and Clock Memory. To use these system memory bits, all we need to do is to check this box, and then enter the address. We should simply check our occupied memory, and then choose an empty byte and use its address. To do this, and to check our occupied memory until now, we can click right on any block, and then select Assignment List. In our case, from the byte number 4, we can use any byte for the system memory bits. We will choose, for example, 100. Since our analog input measurement is from 4 to 20 mA, so we are working with the unipolar mode, that's why, here, we should enter the tag, always false. For the return value output parameter, here we should assign a tag which its data type is word. The returns value parameter serves only to give us feedback of the scale function when it is running. In other words, when the analog input measurement is in the configured range, the RET value returns 0, means no error. But, if the configured range is exceeded, the RET value will return an error code. Since in every call of this function block, every bath will have its own scale function, and then, its own RET value parameter, so, we will create a new local output parameter, its data type is word. Then, we will assign it here. The final output parameter is out, its data type is real. It will contain the final scaled value of the temperature, and through this parameter, we can then read the actual temperature in Celsius degree. Since every bath has its own temperature, we will create a new local output tag. And we define its data type as real, means, floating point. Then, we can drag it and drop it here. We finish with configuring the scale function. We noticed that, when we change the interface of the function block, means we add or delete local parameters, the FB calls will be in red, means they are out of date with the change of the FB interface. All we have to do is, simply, click right, then, update interface call, and the interface call will be updated. Here, we can see the new inputs and outputs of the FB, as we have configured through its interface. We do the same with the second call, click right, then select update block call, then we hit OK. Now, the two calls of the function block are updated with the new FB interface. Let's go back and continue writing the code for the temperature control template. Via HMI, the user has two setpoints for each bath. The first is called setpoint temperature, the second is tolerance. For example, when he wants to control the temperature at 70 degree, with tolerance 1 degree. In result, the thermal resistance will turn on when the actual temperature is lower than 69 degree, and then turn off when actual temperature exceeds 71 degree. So here, through the FB interface, we will define two setpoints as an inputs, its data type are real. In the program, we will not use the setpoint 70 degree, but rather, we will use 69 and 71 degree as thresholds. To calculate the high threshold, we will add temperature setpoint plus tolerance. For example, we will add 70 degree plus 1, to get 71 degree. We used the add instruction. Its two inputs are setpoint plus tolerance. Its output will be a new tag, which is high threshold, or high setpoint. We will define it as static. Static means internal local tag, we don't have to assign it next when calling the function block for each bath. To calculate the low threshold, or low setpoint, we will use the sub instruction. We will subtract the setpoint and the tolerance, to get a new tag as a result. We will define it as static, in the FB interface. Now, it's time to command the output. Simply, we will compare the actual temperature, coming from the PT100 sensor, with the two thresholds. When the bath temperature is lower than low setpoint, the thermal resistor will be on, and its state will be stored as 1, via the set instruction. The thermal resistor will be defined as local output in the FB interface. In result, when calling the function block for each bath, we will assign a different tag for each bath. When the bath temperature is greater than high setpoint, the thermal resistor will be off, and its state will be stored as 0, via the reset instruction. At this point, we finish with creating the code for the FB temperature control. When we go back to the two calls of this template, we notice that they are out of date. Let's click Write as usual and do an update. As you can see, each call of the function block has the same interface, means the same inputs-outputs. Our task now is to assign the related tags for each instance, or in other words for each bath. To do that, we will create a new data block. There, we will create all internal tags related to the two baths. We will give it the name, bath settings. Here we will create all tags related to the baths, including the set points, the tolerances, the temperature converted to floating point. We can create the tags in the data block one below the other, and we can also create our own data type, and then use it for every bath, without repeating the creating of the tags for each one. To create our own data type, we can simply go under PLC data types, and click on Add a new data type. We will give it the name, DataBathX. Next, we will create all the tags needed for each bath. These tags are setpoint temperature, and it is real; tolerance, real; return value, word; actual temperature, real. Once this own data type is created and configured with its data, now we can go back to the data block, bath settings, and now we can define the tags for each bath. As you can see, we can drag this new data type it and drop it here. Now, with a simple click, we can add the same data for each bath. The last task to do is to assign to each bath its related tags. We can simply click on the data block, click on Details View, and then drag and drop the new tags and assign it to the right place. For the int temperature input, and for the thermal resistor output, we assign its related physical tags, already defined in the device configuration. We do the same for the bath number 2. The int temperature and the thermal resistor are physical tags, and all other tags are already defined in the data block. Before we test our code, we can open the settings data block and give the setpoints a starting value. These settings will be configured next via the HMI station. Once it is configured, let's run the simulator and start testing our code. The program is well loaded to the PLC sim. We are online with the virtual controller, and online with the function, FC temperature control. Here we can see the two calls of the function block that we made, with their related inputs-outputs. We can notice also that the set points taken already their configured start values. The int temperature's inputs are 0, since they are physical inputs, and there is no signal because we are in simulation. To test the code, we already advised to create watch table and force table. We will create 2 watch tables, one for each bath, and there we will define 2 tags to watch online and follow their status, real actual temperature, and also, the output thermum resistor. For the bath number 2, another watch table, and there we add the real temperature also, and the output thermal resistor. To simulate the physical inputs, either digital or analog, we use the force table. In our case, we will open the force table, and there, we will add the 2 int temperatures, to force it later. The PT100, through its converter, send an analog signal to the PLC, between 4 and 20 mA. The analog input module converts this signal from analog to a digital signal, comprised between 0 and 27648. Remember this number, 27648. Until now, the 2 temperatures of the baths are 0, that's why their thermal resistances are on. We said that, when the actual temperature is lower than the setpoint low, the output should turn on. Now, when we force the int temperature to 27648, means we have 20 mA in the analog input channels, and as a result, we have 250 degree, our max range already configured. At this value, the outputs will turn off, because the actual temperatures exceeds the SP high for each bath. The test procedure consists of forcing each time the int temperature, and check the behavior of the thermal resistor output. The force value of any analog input should be between 0 and 27648. The next step is to add a screen in the HMI station, where we can check easily the bath's temperature status, and monitor the whole system with simple clicks. The next step is to add a screen in the HMI station, where we can check easily the bath's temperature status, and monitor the whole system with simple clicks. A screen in the HMI station, where we can check easily the bath's temperature status, and monitor. About the settings, each bath has its own temperature setpoint and tolerance. The user can change these values any when he wants. We have also dynamized the color of the heater. If it is gray, means it is off, and when it is green, means it is on. For example, in the bath number 1, if the actual temperature is 45 degree, and if the setpoint is 60 degrees, then the output is on, because, as we programmed it, when the actual temperature is lower than the setpoint minus tolerance, then it should be on. And if we change the setpoint to 40 degree, then the actual temperature will exceed the threshold, and as a result, the heater resistor will turn off. This is the way we test our code. We change the temperature, or the setpoints, and then check the behavior of the output. The same for the bath number 2. We can ensure that, even if the 2 baths use the same function block, or as we named it, template, there is no conflict or overlap between them, since each one has its own instance data block which is unique. To change the actual temperature value, and since we are in simulation mode, we can force the analog inputs, using the force table. Now, we want to display the values of thresholds, setpoint high and setpoint low. They were defined as static, and they exist only in the instance data block of the call of the FB. So, we will change their declaration from static to local output, and then display their values in this screen. To do that, we go back to our function block, then move these 2 tags from static to local output inside the I/O interface of the function block, without touching our code inside. Going back to our function, where we call the function block, we notice that the 2 calls are out of date. We click right, and then, as usual, hit Update block call. As you can see, the two thresholds tags are now in the outputs of the function block. We need to create their related tags, and then assign it in the right place. We will create them here inside this data block, and since we are using our own data type, called dataBathX, we will use it to add these new tags, for each of the two baths. We can go under PLC data types, we open our own data type to edit it. There, we create the new tags, and we define their data types as real. Once it is done, when we go back to the data block, we notice that our own data type is in red, since its interface has changed. To update it, we simply click right and then, click on Update Interface. By doing this, we can ensure now that each of the two baths has two new tags, setPoint high, and setPoint low. Now, we are going to assign them in the related call of the function block. We click once on the data block, then click on Details View, and then assign the tags one by one, for Bath 1, and Bath 2. Since we have modified our code and don't download it yet to the PLC, so as result, the blocks online and offline are different. That's why we see these blue-orange circles. We should download the modifications to the PLC sim. Now, the block offline and online are the same, and we are code updated as well transferred to the PLC. We can notice that the two tags, setPoint high and low, are well working and their values are well assigned. Once we have finished, we move on to the screen in the HMI station. And all we have to do is to assign the I/O fields there to the new tags we have created. These fields will be defined as output, so the user cannot change its values during runtime, he can only read it. We can also set the format pattern, and import the related tag from the PLC station, because they are not yet defined in the HMI station. Once we have finished, and when we start the HMI runtime, we can now see the new tags with their actual values, the setPoint high, and the setPoint low. There is a trick we should learn when we are dealing with settings. When the user change the setpoints during runtime, these values are stored in the related data block. But, when the PLC turns off or it paces to the stop mode, these values are lost, and during its next startup, it will start with the start values, configured in the data block. To resolve this problem of lost data during stop mode or PLC shutdown, there is an option we can use it in any data block. It is called retain. When we activate this option for the settings tags, then the PLC will store their last values, even when it is in stop mode or it is off. After enabling this option, let's download the modifications and see what will happen. Now, when the user changes the settings, and when the PLC goes from run mode to stop, and then from stop to run mode, we can see that the settings are well stored and keep their last values. As we said, this option is highly recommended when we have setpoints that are defined by the user during runtime, and should be stored in the PLC memory even when it is off. The last chapter in this course is the HMI trends. We want to display the trend of the first bath actual temperature. To do that, we are going to create a new screen, and give it the name, Trends. If you want to enable any screen to be the start screen at runtime startup, you can simply click right on it, and then select, Define as Start Screen. Now, we go under, Controls, and we drag and drop this icon called, Trends View. This is an already preset view made by Siemens. It allows to display trends. We have just to configure it. We click right on it, select Properties, and under the sub-menu Trends, we can add many trends in the same view. In our case, we want to visualize the actual temperature of the bath 1, and its two setpoints thresholds, high and low. We click on Add New, and then we can choose the trend color, and for the source settings, we select the source tag of the actual temperature. Next, we add the two other trends, for setpoint high, and setpoint low. Finally, and after starting the runtime, we can see the trend of the bath actual temperature, with the two thresholds, high and low. Now the simulation and the test of our code become more easy and efficient. We can change the temperature, check its position between the configured limits, and also check the behavior of the output. During this chapter, we learned how to create a temperature control system, how to create a function block and how to configure its interface, and then how to call it and use it for 2 calls or even more. We learned also how to create our own data type and then how to use it, and finally how to display trends in HMI runtime. You can download this project. I will give you the download link. The last trick I want to show it to you is how to archive and retrieve a TIA portal project. So this is our current project. We can here check its path, where it is saved. In my case, in desktop, under a folder named My First Project. We can go under this path, open the folder and see how it looks our TIA portal project. It is divided into folder and files. In addition, we have a file that allows us to open the project. Its extension is AP15_1, and 15_1 is the TIA portal version of this project. When TIA portal is closed, we can open the current project by clicking twice on this file. Now, we want to archive this project, and make it under one zipped file, so that we can save it or send it in an easy way. To do that, we go under Project, and we select the option Archive. Through this windows, we select which project to archive, in our case, this current project. And under Target Path, we should select when we want to save the zipped file. We will save it directly under Desktop. We give a name for the zipped file, and then we hit OK. After a couple of seconds, we can see that the archive file of our current project is well created. Its extension is ZAP15_1. So, when you see a file with extension ZAP, means it is an archived project, and the next numbers represent the version of TIA portal. Now, we suppose that you have received this archived project, and you want to retrieve it and then open it. So first, close any open project in TIA portal, and then, open the project menu, and select Retrieve. First, we should select which archived project we want to retrieve. In our case, we have the zipped file that we created. Next, we should select a path where we want to save the retrieved project. We are going to create a new folder, under Desktop. Once we hit OK, and after a couple of seconds, we can see that the project is well retrieved. The most important thing you should know is, to retrieve a zipped project, your version of TIA Portal should be the same as the version of development of this project, or higher. When you will download this project, open TIA Portal and retrieve it as we have just learned. Next you can run the simulations as we did and test it again. Thanks for your time, and I wish you enjoyed this course and learned how to deal with Siemens PLC and TIA Portal.